The ground beneath one of Europe's most densely populated coastlines has been rising for 3 years without stopping. Not centimeters, not slowly. The earth beneath the Phlegraean fields west of Naples has lifted by more than a meter since 2021, and the rate is accelerating. Right now, as you read this, the caldera floor is still moving upward. Scientists monitoring it have begun using a word they spent decades trying to avoid. Critical. This is not Yellowstone. This is not a remote wilderness where the nearest town is 200 miles away. The Campi Flegrei caldera sits inside a metropolitan region of over 3 million people. Naples rises directly along its eastern rim. The towns of Pozzuoli, Bagnoli, and Bacoli sit on top of it. And the underground system driving all of this movement has just recorded the highest stress accumulation in 500 years of documented history. Most people have never heard the name Campi Flegrei. That is not because the system is small. It is because the last time it erupted at full scale, it was the year 1538. But quiet does not mean stable. And what the instruments beneath this caldera are measuring right now is the geological opposite of stable. Let's start with what Campi Flegrei actually is, because understanding the structure is the only way to understand why the current data is so significant. A caldera is not a volcano in the traditional sense. When most people picture a volcano, they picture a cone, a mountain with a crater at the top, lava flowing down its sides. A caldera works differently. It forms when the magma chamber beneath a volcanic system empties so rapidly during a catastrophic eruption that the ground above it collapses inward. What remains is not a mountain. It is a depression, sometimes dozens of kilometers wide, with the remnants of the old volcanic system buried beneath it and a new sprawling hydrothermal network threading through the rock above. Campi Flegrei translates from Latin as the burning fields. The name was given by ancient Romans who noticed that the ground in this area smelled of sulfur, bubbled with boiling mud, and was warm to the touch even in winter. They thought it was the entrance to the underworld. They were not entirely wrong about what lay beneath. The Campi Flegrei caldera stretches approximately 13 kilometers across at its widest point. It formed in 2 major collapse events, one approximately 40,000 years ago and a second approximately 15,000 years ago. Each of those events produced eruptions so large that they left volcanic ash as far away as Russia, the Middle East, and Central Africa. The 40,000-year event, now called the Campanian ignimbrite eruption, is considered one of the largest volcanic events in European history. It blanketed an area of roughly 3 million square kilometers in ash and pumice. Some researchers have suggested its climatic effects may have contributed to the decline of Neanderthal populations across Europe. This is the system that is currently experiencing its highest recorded ground deformation in 5 centuries. Let that settle before moving forward. Since the early 1950s, scientists have been tracking a phenomenon at Campi Flegrei called bradyseism, a slow, rhythmic rise and fall of the ground, driven by the movement of magmatic fluids and gases through the crust beneath the caldera. The word comes from Greek, brades meaning slow, seismos meaning shaking. It is, in essence, the caldera breathing. During periods of unrest, the caldera floor rises as hot fluids and gases press upward through the rock. During quieter periods, it subsides. This cycle has been documented and measured for decades, but the current episode is unlike any in the instrumental record. The ground beneath Pozzuoli, the town sitting closest to the center of the caldera, began rising in 2005. It has not meaningfully stopped since. Between 2005 and 2023, the cumulative uplift reached approximately 1 meter. Then the rate accelerated. In 2023 and 2024 alone, the ground rose by nearly another full meter. The total uplift since the current Unrest episode began now exceeds levels not seen since the crisis of the 1980s, and that crisis forced the evacuation of 40,000 people from Pozzuoli. The difference between then and now is that the 1980s crisis eventually subsided. This one has not. Here is the data point that concentrates scientific attention more than any other. A 2024 study published in the journal Nature Communications, led by researchers from the Vesuvius Observatory and the National Institute of Geophysics and Volcanology in Italy, analyzed the current Unrest episode against 500 years of historical records for Campi Flegrei. Their conclusion was unambiguous. The thermal and mechanical stress currently acting on the rock surrounding the caldera's hydrothermal system has reached levels with no precedent in the entire 500-year record the team could reconstruct. The rock above the magma system is being heated and pressurized from below. The critical question, the one that determines whether the current unrest leads to an eruption or eventually subsides without one, is whether that rock can hold. And what scientists now know about the specific geological structure beneath Campi Flegrei makes that question significantly harder to answer than it would be for almost any other volcanic system on Earth. Beneath the caldera floor sits a hydrothermal system, a network of superheated water, steam, and volcanic gases percolating upward through fractured rock. This system is not new. It has been active for thousands of years. But what the current uplift episode is doing to it is new. As the caldera floor rises, the pressure regime throughout the shallow crust changes. Rocks that were previously in compressional equilibrium begin to crack. Fractures that were sealed by mineral deposits over centuries are being forced open by the movement. And as those fractures open, they create pathways for the pressurized hydrothermal fluids to migrate upward into shallower, cooler, and more brittle rock. This is the specific mechanism that researchers are watching most carefully, because there is a threshold in this system, a depth and temperature at which the rock transitions from behaving in a ductile, flexible way, absorbing stress by deforming gradually, to behaving in a brittle way. Brittle rock does not deform gradually, it fractures suddenly, and a fracture propagating through pressurized hydrothermal rock at Campi Flegrei is not just a geological curiosity. It is a potential pathway for an eruption. The 2024 Nature Communications study specifically modeled the depth at which the brittle-ductile transition zone currently sits beneath the caldera. Their finding was that the boundary has been rising, moving upward toward the surface, as the hydrothermal system beneath it has been heating and pressurizing the overlying crust. In practical terms, this means that the zone of rock capable of suddenly fracturing is now closer to the surface than it was 5 years ago, and it is closer to the surface than at any point in the 500-year record the study examined. But there is something else in this data set that is equally important and rarely discussed in coverage of Campi Flegrei: the earthquake swarms. Since 2023, the caldera has been experiencing earthquake sequences of increasing frequency and in some cases increasing magnitude. On September 27, 2023, a magnitude 4.2 earthquake struck beneath the Campi Flegrei caldera, the strongest event at the site since the 1984 crisis. It was felt across Naples. It was felt on Ischia. People ran into the streets. In the weeks that followed, hundreds of smaller earthquakes rattled the caldera floor. Then, in May 2024, a magnitude 4.4 earthquake, larger still, struck beneath Pozzuoli. The shaking knocked plaster from buildings, cracked walls, and sent residents flooding into the streets and parks for the second time in less than a year. Italy's Civil Protection Department issued formal guidance on eruption scenarios. Emergency response plans that had existed on paper for decades were quietly updated and activated. The European Commission funded an accelerated review of evacuation infrastructure for the Campi Flegrei red zone, the area of highest risk surrounding the caldera. These are not precautionary bureaucratic exercises. These are the responses of governments and scientific agencies that are reading the same data and reaching the same uncomfortable conclusions. The red zone around Campi Flegrei currently encompasses approximately 500,000 people. The yellow zone, the next tier of risk, encompasses another 800,000. And beyond those designated zones, the city of Naples itself, with approximately 1 million residents, sits directly on the eastern rim of the caldera. In a large eruption scenario, the question is not whether Naples would be affected. It is how severely and how quickly. Now here is the part of this story where the historical record becomes both instructive and deeply uncomfortable. The last eruption at Campi Flegrei did not happen in ancient times. It happened in 1538. On September 29th of that year, after a period of ground uplift and seismic activity that lasted several years and drove much of the population of Pozzuoli to evacuate the town, a new cone began to rise from the caldera floor near the edge of Lake Avernus. Over the course of approximately 1 week, this cone grew to a height of approximately 130 meters. It erupted explosively, scattering ash and debris across the region. Monte Nuovo, New Mountain, is what the local population named the cone that formed in that week. It still stands today. But here is what the 1538 eruption tells us about the current situation that no modern instrument can directly measure. The precursor Unrest before the 1538 eruption began years before the eruption itself. Pozzuoli experienced significant ground uplift. Earthquakes disturbed the region. The sea along the coast changed color as volcanic gases bubbled up through the sea floor. Fish died in the harbor. Then, after that prolonged period of unrest, the ground subsided again. People began to think the danger had passed. They started moving back into their homes. And then, within days of that apparent subsidence, Monte Nuovo erupted. The pattern of unrest, apparent stabilization, and sudden eruption is not unique to Campi Flegrei. But it is a pattern that the system has demonstrated at least once in its documented history. And it is a pattern that gives volcanologists particular reason to be cautious about interpreting any pause in the current unrest as evidence that the system is returning to equilibrium. The eruption of 1538 was, by the standards of what Campi Flegrei is capable of, a relatively small event. A single cone, a single vent, explosive but contained. The system's largest historical eruptions operated on a completely different scale. The eruptions that formed the caldera itself, 40,000 years ago and 15,000 years ago, ejected volumes of material measured in hundreds of cubic kilometers. They blanketed continents in ash. They altered the global climate for years. A repeat of those events is not what scientists are primarily concerned about in the near term. The system would have to be much closer to a full magmatic recharge to produce an event of that scale. But there is a wide spectrum between a Monte Nuovo scale eruption and a caldera-forming super eruption. And somewhere on that spectrum sits the range of scenarios that current data cannot rule out. Researchers working on eruption scenario planning for Campi Flegrei typically model events in 3 broad categories. A phreatic or hydrothermal explosion driven by the sudden flashing of pressurized water to steam rather than by a direct magmatic connection to the surface. A phreatomagmatic eruption, where rising magma interacts with the groundwater and hydrothermal system to produce a highly explosive blast. And a fully magmatic eruption, where molten rock reaches the surface directly, either through a new vent on the caldera floor or through reactivation of one of the existing vents within the system. The current data does not confirm that any of these scenarios is imminent. It does confirm that the conditions necessary for any of them to occur are more developed right now than at any point in the 500-year observational record. That is not the same thing as predicting an eruption, but it is a very different thing from saying the system is stable. Here is the logistical reality that makes the scientific situation at Campi Flegrei particularly acute. Evacuating the red zone around Campi Flegrei is a problem that Italian civil protection authorities have been modeling and testing for years. And every honest assessment of that problem reaches the same conclusion. Moving 500,000 people out of the Campi Flegrei red zone in a time frame that volcanic unrest might provide days, not weeks, through a road network shared with the greater Naples metropolitan area is one of the most complex civil emergency operations in European planning history. The roads leading north out of Pozzuoli pass through Naples. The coastal highways that skirt the western edge of the caldera are narrow and prone to congestion. The rail lines serving the region were not designed to evacuate populations at crisis scale. And overlaying all of this is the fact that in a scenario where the caldera is actively accelerating toward eruption, the ground shaking from the associated earthquake swarms could be damaging or blocking the very roads that evacuation depends on before evacuation can be completed. Italian authorities have been running evacuation drills in the Campi Flegrei red zone since 2019. The most recent large-scale exercise took place in May 2024, just days after the magnitude 4.4 earthquake. The drill involved approximately 10,000 residents and tested the evacuation of a single municipality within the red zone. The scale of an actual emergency would be 50 times larger. The gap between the drill scale and the real scale is not a criticism of the authorities running it. It is a reflection of the genuine difficulty of the problem. There is no easy solution to evacuating a metropolitan area of 3 million people from a volcanic system that can transition from background unrest to active eruption on a timescale that no current monitoring system can predict with precision. What monitoring can do, and what the Vesuvius Observatory's continuous instrumentation network is doing around the clock, is detect changes in the rate and character of ground deformation, seismic activity, and gas emissions that would indicate the system is approaching a point of critical change. The current monitoring infrastructure at Campi Flegrei includes GPS and INSAR satellite deformation tracking, seismic networks covering the entire caldera and surrounding region, gas emission monitoring stations at fumarolic vents, including the Solfatara crater, seafloor sensors monitoring changes in the submarine portion of the caldera, and tilt meters and gravimeters tracking minute changes in the geometry of the volcanic edifice. This is among the most densely instrumented volcanic systems on Earth. And what all of those instruments are collectively telling scientists is that the system is in a state of escalating, sustained unrest, with no clear sign of returning to the lower energy background state that characterized the caldera between the 1980s crisis and the early 2000s. The Solfatara crater, which sits in the eastern portion of the Campi Flegrei caldera and has been a major tourist destination for centuries, has been closed to visitors since 2017. It was closed following the accidental death of a tourist who fell through the thin crust of the crater floor into the boiling mud beneath. But since that closure, monitoring data from Solfatara has tracked a steady increase in the temperature and flux of gases escaping from the crater's fumaroles. Carbon dioxide and hydrogen sulfide emissions have risen. Water vapor output has increased. The temperature at the main fumarole vent has climbed. These are not dramatic visible changes for someone observing from outside. They are the kind of changes that show up in data streams rather than in photographs. But they are the changes that volcanologists read as indicators of increased heat flow and pressurization from depth. The hydrogen sulfide data is particularly telling. Hydrogen sulfide is released when magmatic gases rising from depth interact with sulfur-bearing rocks in the hydrothermal system. An increase in hydrogen sulfide emissions is a signal that the magmatic gas flux from depth is rising, that more material is moving upward through the system from the magma reservoir below. This does not mean magma is at the surface. It means the conduit connecting the deep magmatic system to the shallow hydrothermal system is more active than it was, and a more active conduit means more heat, more pressure, and more mechanical stress on the rocks containing the system. This is the feedback loop that researchers are most concerned about. More heat means more hydrothermal activity. More hydrothermal activity means more pressure on the surrounding rock. More pressure on the surrounding rock means more fracturing and more earthquakes. More fracturing means new pathways for fluids to migrate upward. And as fluids migrate into shallower, cooler rock, they can interact with groundwater in ways that further destabilize the system. It is not a runaway process. Each step in the chain has its own timescale and its own uncertainty. But it is a directional process, and the direction it has been moving since at least 2005, with the acceleration observed since 2021, has been consistently toward higher energy, higher stress, and higher risk. Here is the question that every honest scientific assessment of Campi Flegrei eventually arrives at and then stops. Not because scientists are reluctant to engage with it, but because the data, despite being extraordinarily detailed and continuous, cannot answer it with the precision that the question demands. Is this the Unrest episode that ends in an eruption? The honest answer is that no one knows. Volcanic systems at this scale have been monitored with modern instrumentation for decades, not centuries. The sample size of major caldera unrest episodes that have been watched in real time with current technology is small. The range of outcomes, subsidence without eruption, long-term simmering unrest, phreatic explosion, full magmatic eruption, is wide. And the specific trigger conditions that would move Campi Flegrei from its current state to an erupting state are not fully understood. What the researchers publishing in Nature Communications in 2024 could say, and did say explicitly, is that the system has now passed beyond the range of conditions documented in 5 centuries of historical records without producing an eruption. That does not mean eruption is certain. It means the system is in territory where history provides no direct precedent for the outcome. It means the scientists watching it are watching something genuinely new. And it means that the 3 million people living within and around the Campi Flegrei caldera are living right now in a situation that has no modern parallel in Europe. The last time a comparable population lived on top of a volcanic system showing this level of unrest was before modern monitoring existed, before evacuation planning existed, before the instruments existed that could track what the ground is doing in real time. In that sense, the current situation at Campi Flegrei is a genuinely unprecedented experiment, not in the laboratory sense, in the sense that humanity has never before watched a system like this closely, at this level of unrest, with this density of people above it. What happens next will be written by the geology, but it will be read by 3 million people who live close enough to feel it. And the most important piece of information in this script is the question that nobody, not the Vesuvius Observatory, not the Italian Civil Protection Department, not the researchers whose papers have reshaped how we understand this system, can yet answer. The ground is still rising, the rate has not slowed, and the boundary between the rock that bends and the rock that breaks is getting closer to the surface with every passing month. At what point does the rock decide it has held long enough?